There's different types of neutrinos too, different sizes and stuff. Um, but they're basically just massless, or not massless. They have very, very small masses, enough to hold the two gluons together, but they're chargeless. It's really hard to detect them. But for every single one of these 6 particles, there's an antiparticle that we'll talk about. There's a positively charged electron called a positron. There's antineutrinos. And what happens with these is that when an antiparticle and a particle, or antimatter and matter, come together, they basically annihilate each other and just produce pure energy. And that's where the E equals mc squared comes from, is that 2 mass particles can come together and be stored as energy, and a tremendous amount of energy, for that matter. Anyway, continuing. So we'll get back to all this in detail when we cover nuclear physics, but that's a little introduction to nuclear physics. Let's go back to field physics. All right, so fields at work. There's 2 different things that we can do that are often asked about fields at work. It's orbital velocity and escape velocity. So and we're going to focus back on gravity and electrostatics. We'll do nuclear stuff later. So for orbital velocity, that's the speed that would be required for an object to completely circle or orbit another object. So this is an example of a satellite orbiting Earth, a distance of r away. And that r is the distance from the center of the Earth to the center of the satellite. So the way you figure it out for gravity is that you set the centripetal force, mv squared over r, equal to the force of gravity, gmm over r squared. Now, some of this stuff cancels out. One of these m's goes away, and so you would get mv squared over r would equal gm over r. Oops, I forgot to cancel out one of these m's. You get v squared equals gm over r. One of the r's goes away, and when you rearrange this equation, you can solve for v, where v would equal the square root of gm over r. Like I said, this mass shouldn't be there, and that's the equation that they give you in the formula packet. For electrostatic force, you can also have like proton or electrons orbiting protons. Similarly, in a circular orbit, there you would set the centripetal force equal to electrostatic force instead of the force of gravity. So instead of setting mv squared over r, you would set instead of equal to gravity, you would set it equal to kq over r squared. This one doesn't simplify quite as nicely, but this would be the mass of the orbiting object. This would be the velocity of the orbiting object, Coulomb's constant, charge of each object, and distance between them. One of the r's goes away. This r would cancel out one of these r's. Now, recall back to circular motion. Circular motion, v is equal to 2 pi r, the distance around the circle, divided by t, the period, the time around the circle. That comes from circular motion, omega being 2 pi over t. So that's for orbital velocity. For escape velocity is basically the amount of speed needed to completely remove the object from that orbit. So imagine if you had the satellite here, or not satellite, but rocket here on Earth. At some speed it's going to orbit, but at some faster speed it's actually going to leave and not come back. So what you do is you set the kinetic energy, which is the moving energy of the object, equal to the potential energy, gravitational potential energy. For electrostatic, you set kinetic energy equal to electrical energy. So what you end up with is, for gravity, you get 1/2 mv squared equal to gmm over r, which simplifies to the escape equation. Escape velocity is 2 times g times m over r, where r would be the distance away from the object, or like the radius of the object. G would be the gravitational constant, m would be the mass of like the Earth in this example, and v would be the escape velocity, the minimum speed you would need to remove something from this planet. Similarly, you could do the same thing for electrostatic. You would do kinetic energy equals electrical energy. If you knew the charges and the distance or the radius of that charge, you could figure out how fast does like an electron have to move in order to fly away from like a nucleus of an atom, for example, by setting these 2 things equal to each other. So let's try some of these out. We'll try some of these out in the next video, or next part of the series, so stay tuned.